Hello everyone, my name is Golnaz Habibi. I am currently Assistant Professor in Department of Computer Science at the University of Oklahoma. Today I'm talking about the data science for safe and resilient autonomous navigation in highly dynamic environment. First of all, I want to talk a little bit more about the application of the data science and data-driven algorithms in robotics and AI. For the robotics, we can see that a lot of application today we see everywhere. For example, we can have the robots for saving lives. For example, in this picture, you see that, for example, surgical robotic system or even self-driving cars, that we can see that by having these applications, we can save human lives and also improve and increase the safety. We also can have robots as entertainment. For example, Skydio for drones for capturing the images and figures, and also we have the Intel here in this picture for creating some interesting formation of the robots and drones. So there are many applications, and also we have the service robots. For example, Kiva from Amazon for delivery robots, package delivery robots, and also Boston Dynamics that can serve as a military or rescue and different applications of the robotic system. Although there are progress in robotics and AI and data-driven algorithm, but still there are numerous challenges that we want to discuss today and how we can tackle these problems. For example, transferability. Assume that we learn the robotic system and your navigation in a specific data set, for example, inside an indoor environment. However, you are interested in, for example, have the navigation and your robot running and performing other space and different environment compared to the data, the environment that you train on. And also we have the robustness, for example, issue that, for example, the idea is that how we can have the model behaves still accurately and efficiently when we have some noises or some uncertainty and even adversarial attack. For example, this adversarial patch, you see that in the traffic signal that makes it actually the neural network to predict or detect inaccurate signal. And we have also interactability. So the goal at the end of the era of AI is to having the AI to be interactive with the human beings and interacting together, so how we can have a team of the agent and AI agent that they can work together, and of course how we can share the data and analyze the data together and exchanging this data information between the two agents and multiple agents is crucial, and still there are many challenges there. So today we are talking about all these topics and how my research address all these areas and these challenges. First of all, I would like to talk about the robustness and certification. What does it mean here, this robustness, and why it's important? In general, recent advances in neural network and learning-based methods leads to efficient algorithms in the robotics and navigation. However, we lack the lack of the robustness in neural network in the presence of the adversarial attack makes this model very vulnerable and sensitive to the noises and adversarial attack. And also, as we mentioned before, if the data distribution in the training phase is different from the data that you test on it, for example, different environment, different sensing, and different parameters, makes it actually your model not very reliable in your testing environment. And also, of course, other problem would be specifically for the safety, it's critical domain. For example, here running the autonomous driving cars or the robots, it makes it problem that when we have the safety critical domain, these areas of self-driving scenarios, of course it would be very difficult and it's not safe to have this model trained on the real data sets. Instead, we use a simulation for the training purposes, and then but we need to transfer this model to the real environment. So having this transferability from the from the simulation environment to the real environment is a challenging problem. In terms of the the robustness and measuring the robustness, how we can measure this robustness of neural network. Our idea is that here, that for example, assume that we have a drone here and we wanted the drone to follow the path, the blue path, but of course, because there's some uncertainty on the model that this drone is trained on it, and also uncertainty in the sensing and the environment, for example, the obstacle here, the red polygons here, that all this uncertainty around the environment as well as the model makes this model with some uncertainty behavior. So uncertain behavior here showing with the bounding boxes. So it means that instead of the drone follow the path, it maybe follow, it had been in any location in these bounding boxes. But the question is that how we can still verify our model is safe enough, and the idea is that if this bounding boxes doesn't collide with obstacles and still it leads to have the drone at the goal destination, we say that our model is verified to be safe. But the challenge here is that because this model is nonlinear and is from neural network, the output and the model that we consider is nonlinear. So given some input boundary and input space, so it gives us actually nonlinear output, and it usually is difficult to measure or estimate this output of this neural network in an amount of time, and usually is not efficient, it's very slow. So our idea is to how we can trade off between the accuracy and efficiency by having algorithms still accurate but efficient enough to we can run it in real time. So here we show that out of our examples that how we can tackle this problem and how our new algorithm solve this issue and improve the accuracy and improve the efficiency as well. So on the left side, the previous algorithm showing that a lot of conservativity in the red agents. We have two agents. We have the blue one that with our adversarial agent, and we have the red agent that tries to avoid the blue agent, but the red agent doesn't know about exactly the location of or the position of the blue agent, which is adversarial. So the previous algorithm, because they cannot accurately measure this uncertainty and the position of the blue agent, and basically it's very conservative in its acting behavior, and we see that how it's far from the straight path. On the other side, our algorithm, it shows that improvement in conservativity. So we have low conservative algorithm, so it follows the shorter path, but still it's avoid the blue agent as an adversarial agent that tries to hit our red agent. And we show that our algorithm is 22% faster than the previous algorithm. After we talk about the measuring the robustness, we also interested to talk about the transferability and lifelong learning. So what is this actually? So current AI actually are very task specific and not generalizable to new domain on task. So the ongoing research now is on the transfer learning. It means that how we can transfer our knowledge across different tasks or environments. And the continuous learning, it says that how we can this transferability basically based on our new domain and also over the time. So we can still have update model over the time, and we can use the transferable model to improve and update our model. So in this work that we see that based on we have the transfer learning and continual learning for motion behavior prediction of the pedestrian. So and specifically we interested in predict the pedestrian location position in highly dynamic environment. And also we see that we extended to continual learning to improve the decision making in reinforcement learning. So in terms of the pedestrian prediction, motivation for that is that many advances, we have a lot of advances in object tracking, but still there are many questions that we have and remain in basically in prediction side, because prediction of the pedestrian usually it has include a lot of uncertainty in the pedestrian behavior. They may change their direction abruptly and they move very quickly. So also they usually don't follow a specific rule on being, for example, in a specific boundary or in a specific road, like similar to the cars or cyclists. So that's what make it all this problem is more challenging to predict the pedestrian behavior. What our idea is? Our idea is how we can incorporate transferable features to learn motion behaviors across different environments. For example, in the specific environment that we are interested in, intersections, how we can have the model that we can transferable across different intersections with different geometry. How we solve this problem is basically we assume that we have the intersection corner, and then we want to show that our algorithm is based on the transferable features, and the features that we pick here for learn our model is traffic light, pedestrian traffic light, and the distance to the curbside. We use these transferable features by using a specific distance measurement to the curbside that make it transferable across a domain, such that, for example, we have two trajectories in two different intersections, as you see, with different colors and with different geometry. Although these trajectories are different in shape in geometry here, but they both of them presenting the same behavior, the same intent, which is turning left at the intersections. So the idea is that how we can have transferable environment such that we can basically move that to other environment. So how we could do that, actually basically we do based on the our model that we learn, so that such that we learn the model over the time, and every time we have a mini batch of the data set that we learn from that, and then what we do is we actually fuse this model by using graphical model. And how we fuse based on some threshold and some similarity. When we have a similarity between two motion prediction and motion primitives, we can fuse it other than the otherwise we actually add the new data set and the new model. So we have that, and we can fuse, for example, these two graphical model and graphical representation of the motion primitives and other transitions, and we have a new model. We can just keep continuing this model and these behaviors, and we can see that how we can continuously learn. What we do is how we use it in our model. We first collect the data. How we collect the data? We collect the data by two platforms. One of them is we use a golf cart, which is included and equipped by two set of the 2D lidar and 3 cameras on the top of on the front of the car, and also we have the velodon, which is a 3D lidar and 6 cameras that we use in the tripod. And as a result, we see that our algorithm and we collect the data in 4 different intersections, and then we predict the trajectories of the pedestrian in the 5th intersections. Even the new intersection was not seen with the agent. We see that our algorithm predicts well and also incrementally improves, as we see that the prediction error that shows that how our algorithm is accurate compared to the ground truth is improving. And also our algorithm showing here that is the best algorithm and closest one to the ground truth, which is the red and yellow -1, and our algorithm is blue one. It shows that our efficiency and accuracy of our algorithm. We extend our work that instead of just using 2 models, we have the multiple models, and by having this strategy and improving our algorithm and extending that, now instead of having 2 models that is fused, we can have a multiple models that it can come from different car. So for example, we have different vehicles that they collect the data and they learn by themselves individually, but how we can fuse this model in an efficient fashion such that we have a scalable model for fusing. And this algorithm shows that very scalable and much faster compared to the algorithm that they use the batch size of the data and a centralized learning. After we talk about basically the robustness and the transferability, we talk a little bit about the interactability and multi-agent systems. Multi-agent system today has a lot of applications, for example, in the transportation, construction, even the self-driving cars for connected vehicles, and even in the games and entertainments. But the problem that we have for the multi-agent systems that usually is not scalable to large number of the agent, and usually the communication, that's the issue, and usually never be addressed very well in the larger scale of the teams. So our approach that how we can actually have a good mechanism for share the data in a distributed fashion and establish a robust communication with efficient data exchange and distributed learning framework. So how we do that, we use our robotic system. Here you see that it's equipped with some grippers, and they use like infrared sensors for measuring the distance as well as the measuring the angles and heading with other agents and other robotic system. And in this video you see that how it's actually working in this environment. So we have a set of robots set up. So they do first explore the environment and find and cover the environment, then a set of the robot actually attach the object as you see here, and then they measure some dimension of the object to create a path. When the path is generated, which is a safe path throughout this robotic system, then this robot is navigating the object and carry the object to the goal destination. We also show that our algorithm is extended to the sim to real transferability. This one video shows that how algorithm is working in the simulation environment for the fencing problem. How, for example, one robot on the left side tries to protect the robot on the left from the heating from the robot from the left side, and we run it. Algorithm and showing them this video that how actually we can transfer this knowledge from the simulation to the real environment. This example showing that the robot is trained actually on the simulation, but how we can transfer our model to the real environment, and now we can have the human is playing with the robotic system. Although all of these advances in robotics and automation and data-driven systems, still there are many challenges here. So we talk about transferability, adaptability, and communication in general for having the robotic system and AI to bring into the real world. However, we still have some issues, and most of them is related to trustness, verification, and explainability of the data-driven systems. And also, we want to see how to have a model that be low cost, can be used and affordable for any person, and also we want to have improve the safety and resilience of the model, especially the human robot interaction scenarios. And as of course that scalability and adaptability of the multi-agent system is still a big challenge that we are having ongoing research on that. We continue this research in my lab. So I would like to also talk about the hiring opportunity in our lab. So we are hiring now in Autonomous Interactive Robotic Lab at University of Oklahoma. And our object is to design and build a collaborative team of ground and aerial robots that navigate and accomplish tasks in realistic environment with the application of the search and rescue, service robot, or self-delivery robots, transportation, and mapping. And we are interested to hire students in the domain of machine learning, reinforcement learning, multi-agent systems, and robots control and navigations, as well as self-driving cars and computer visions. So if you are interested for the PhD position in computer science, please send your CV and transcript to my email. So we're looking forward to working with you and keep in touch. Thank you so much. I really appreciate your attention. Thank you.